In this lesson, we're going to be looking at content in Chapter 3, Section 6. We're going to be solving polynomial inequalities. We've been solving polynomial equations where we have an equal sign, but now it's time to look at polynomial inequalities. A polynomial inequality is any inequality that can be put into one of these four forms. Okay. F of x, or the function we're working with, is less than 0, or we might be looking at the case where f of x, the polynomial, is less than or equal to 0. We might be looking at where the polynomial function f of x is greater than 0, or f of x is greater than or equal to 0, where f of x is a polynomial function. So just revisiting this notation right here. So if we have a polynomial and it's less than 0, we can also think of that as being called as negative. Less than 0, think of numbers that are less than 0. Those are negative. Another way to think of this is, where is the graph of our polynomial function negative or below the x-axis? This notation right here is, where is the function negative or equal to or on the x-axis? So this is negative or equal. Negative, or we'll say on the x-axis. This right here, f of x is greater than 0. Think of greater than 0 as positive numbers, so we'll say positive. Or we can think of where the graph is above the x-axis. So the x-axis is going to divide the graph into a couple different parts, where the graph is above the x-axis or below the x-axis. And then of course we want to also consider where the graph is on the x-axis. So where is the function above or positive? Where is the function above or equal to or on the x-axis? We're actually going to be restricting our view of inequalities, of polynomial inequalities, to more specifically quadratic inequalities. So our highest exponent that we'll be dealing with in this content is when the exponent is 2. All right, and just some background. The x-intercepts of the quadratic function are called boundary points. It's where the graph lies above the x-axis and where the graph lies below the x-axis. So for this graphical example right here, we have two x-intercepts. We have an x-intercept at x equals 1 and x equals 7. And so if we think about taking those two x-intercepts and dividing up the x-axis into regions, we can say that the intervals that are formed by these two x-intercepts create 3 sections, from negative infinity up to 1. And then also we want to consider between these two boundary points, or x-intercepts, the interval from 1 to 7. And then the third region created by these two x-intercepts is that region, that interval where x goes from 7 to infinity. So boundary points divide the function into regions. So for this example right here, the red region of this graph is above the x-axis, and that corresponds to where is the function above or greater than 0. And so you can see that all the y values on these points that are in red, they're all going to contain y values that are positive because I'm above the x-axis. So for our graph right here, the blue region of the graph falls below the x-axis. So that would be translated to the notation, where is f of x less than 0 or negative or below the x-axis. And we can see that any point we choose that would be on this blue part of the graph, the y-coordinates would be negative to get us underneath below the x-axis. So the x-intercepts of the function divide the number line into intervals. So we saw that down here. On each individual interval, the graph of f is either above the x-axis, with this notation above, or below the x-axis. So on each interval, so from negative infinity to 1, let's just kind of cover up that part that's not applicable. From x equals negative infinity up to 1, the entire graph right here, this, not the entire graph, but this part of the graph would be above the x-axis. Now let's look between x equals 1 and x equals 7. Any x value that falls between x equals 1 and x equals 7 would get us to a point on the graph that falls below or is less than 0. And to conclude, when you look at the third region created, the whole part of this graph right here is above the x-axis. So here are the steps to solving polynomial inequalities and what we're going to be doing. First thing is we want to set the equation equal to 0, if it's not already done so. The solutions, or the x-intercepts, are called the boundary points. So what we're going to have to do is solve the polynomial by factoring or quadratic formula to get the x-intercepts. Remember, those are also called solutions or roots. Okay, after we set the equation equal to 0 and we solve and get the boundary points, we're going to locate the boundary points on a number line. And then this will divide the number line into intervals, like what happened up here. Step 3, we're going to choose a representative number called a test value within each interval and plug that x value back into the function. When we plug that x value or that test value back into the function and the answer comes back positive, then we know in that interval that the graph would lie above the x-axis. If we plug that x value back into the function and it returns a negative number, like if I chose any x value from 1 to 7, like 2, 3, 4, 5, or 6, I'm going to get back, when I plug in one of those numbers to this equation, I'm going to get a negative result. So that means that the whole entire graph, that part of the graph would fall below the x-axis on that interval if I get back a negative number. And the fourth step is we're going to write the solution set two ways using interval notation. And then we're also going to draw a number line to represent the solution set. All right, right here we have an example. It's pretty much worked out. We'll add a few details. But so example 1, this is a polynomial inequality. There's no equal sign here, so we don't call it a polynomial equation. This is a quadratic inequality. All right, so step 1, set the equation equal to 0, or one side of the equation, set the inequality to 0. So it is already solved for 0, or set equal to, or less than 0, one side is. So then the next thing is, let's replace that inequality symbol with equals. So we'll do a factor sum chart. We'll factor it. It's a pretty easy factor because a is 1. Once we set each factor equal to 0, we know from this factor we get a solution of 1, and we also get a solution of 7. So these are our boundary points, solutions, x-intercepts. So step 2 was locate these boundary points on a number line. So we'll draw kind of a quick number line. We'll label 1 and we'll label 7. So let's put a point here at x equals 1 and a point here at x equals 7. So we located the boundary points on a number line. Next thing, we're going to choose a test value within each interval and plug those back in, evaluate the function at that number. All right, one thing else I might do here is at these boundary points, I'm just going to put a 0 above them because these are my zeros, or my x-intercepts of this polynomial. All right, so this is kind of worked out for us. It says choose a test value within each interval. So we consider from -infinity up to 1, so the interval -infinity up to 1, a number, x value that's in that interval is 0, and that's always a good value to test. So I'm going to plug 0 in to the polynomial. So f of 0 is equal to 0 squared minus 8 times 0 plus 7. We do this on our calculator. Notice the number is positive. So f of 0 is greater than 0. So we're going to come up here because we chose to plug in 0, which is in this interval. I know my answer is going to be positive, which any other x value within this interval from -infinity to 1, even if we plugged it into the problem up here, we're going to get all positive answers. Now, what we're doing is we're just confirming this graph that we have up here. So notice that the graph of this polynomial is above the x-axis, or positive, from -infinity up to 1. So that should confirm down here numerically what we see graphically up here. All right, the next interval goes from 1 to 7. So it doesn't matter what x value you choose. The test value is 2. So let's plug in 2 for all the x's in our polynomial. And when we do that, we get a negative number. So f of 2, which equals -5, is less than 0. So here's 2. I would put a negative for every x value between x equals 1 and x equals 7. And we can see from our graph that from x equals 1 to x equals 7, my whole graph is negative or below the x-axis. The y-coordinates, which we just found, are negative. And the last interval is 7 to infinity. Let's choose 8, plug in 8, do the work. We get another positive number. So at 8, I would put a plus, and everything within that interval from 7 to infinity would be positive. All right, now we're going to use this first number line right here to organize our answers. So it says, write the solution set using the intervals that satisfy the given inequality. Use interval notation. Include the boundary points of the inequality if the inequality contains the or equal inequality symbol. All right, so here's our solution. So what we have to do is we have to go back to the original problem. And remember, this is f of x, and this is less than 0. So we want all the negative answers. So interval notation that contains the interval answers for the x's. So our answer is going to be 1 to 7. So this is one of a two-part answer. The second part is, let's graph this interval on another number line. So I would just label 1 and 7. Okay, and on the number line, I want to use parentheses here at 1 and 7, and I'll darken in all the x values between x equals 1 and x equals 7. So this is interval notation that represents the solution set on the graph. All right, we're done with this example, but I do want to say, well, what happens if this symbol wasn't less than? What if it was something else? What if, I'll put that down here. What if x squared minus 8x plus 7 was supposed to be greater than 0? So once I did all this work, the last thing I do is I go back and I remind myself, what was the inequality? Because by this time I've forgotten. So the inequality is greater than. So I go back to my organized work and I go, okay, greater than 0 means positive. So coming up from negative infinity, the solution in interval notation would be negative infinity up to x equals 1, union. All these values return a negative, or all these x values return a negative y, so I don't want those if my inequality was greater than 0. And so I go back to 7, I don't include it, and I go to infinity. Okay, so the solution would look a little bit different. Let's look at the number line solution. So this is interval. I would still put 1 and 7. Okay, but now for the positive solutions, I'm coming up from negative infinity to 1. So I'll draw my parenthesis this way so I can darken in this part of the number line. I don't want to include 1 to 7, but I do want to include from 7 to infinity. So this is interval notation, and this is the graphical representation of on a number line of that solution. Okay, let's do one more. What if the original problem had greater than with a polynomial f of x is greater than or equal to 0? Well, remember, these are the greater than, but we did not include where the graph was actually equal to the zeros above x equals 1 and x equals 7. So our interval notation would just have us go from negative infinity up to 1, but we want to include the 1. Because at x equals 1, we get a 0, and the or equal to means we can include it. And then we'd put a bracket here on the 7. All right, and then the number line, the adjustment, would just be that I would have brackets at x equals 1 and x equals 7, but still with the highlighted or darkened parts of the number line here. All right, let's look at another example where they've kind of gotten us started, but we've got to finish it. All right, here's example 2. Let's solve this polynomial inequality. Well, it's not set to 0, so we're going to subtract the 20 here, and we'll put a subtraction of 20 here. So we get x squared minus x minus 20 is greater than 0. Step 1, replace the inequality symbol with equals. We'll do a factor sum chart. Set each of these factors equal to 0. So we get the solutions or the boundary points of positive 5, negative 4. Immediately we'll draw a number line. We'll put negative 4, and I'll put a 0 above it. That's the x-intercept of the 0, and I'll put 5 on the number line. It's a boundary point with a 0 above it. So now we have the interval negative infinity to negative 4 to test. Negative infinity to negative 4. Then we need to test an x value within negative 4 to 5. And then our last test interval will be from 5 to infinity. So the work's done for us here. The test interval from negative infinity to negative 4, we chose x equals negative 5. Go to the original problem. If x is negative 5, actually I'm going to go to where the equation is set equal to 0. So plug in negative 5, square it, minus a negative 5, minus 20. All this can be done on the calculator, and we end up with 10, a positive number. So that means that we have positive values on this first interval from negative infinity to negative 4. So I'm just going to record several positive signs here. Okay, let's look at our next test interval from x equals negative 4 to x equals 5. A good number, quick number to evaluate and test would be x equals 0. So I'm going to plug in 0 to the original problem, do the work. I get a negative answer. That means I'm going to have negatives in between. The last test interval is 5 to infinity, so let's just choose 6, plug it into the equation, and we get a positive number, so we're going to record pluses here. Okay, we're not done until we tell somebody what the answers are. The answers are going to either be the positive solutions or the negative solutions. Because remember, inequalities, they refer us to either positive or negative solutions. So let's go back to the original problem now. So actually the problem, I said that again, but the problem where I set one side of the inequality to 0. So remember, this is f of x. We're looking for where the y values are above the x-axis or positive. So these are my solutions right here. So the solution would be contained to this inequality would be contained on the intervals from negative infinity to negative 4 and then 5 to infinity. Parentheses, because we don't have the or equal or the little line here. Okay, we have to do two things. Here's one part of our answer and the other part is the graph. So again, I'm going to put negative 4 and 5. I want to include values from negative infinity up to negative 4 with a parenthesis. So I would darken in this part of the number line. And then I don't have solutions again, x values that give me positive answers until I get to 5. So I'll do a parenthesis at the 5, and then we'll darken off to infinity this way. All right, time for us to try a couple of examples. So looking at example 3. Okay, I'm supposed to solve this polynomial inequality. Step 1, set to 0. Good, it is. Step 2, set the polynomial inequality to equals 0. Make a polynomial equation. All right, let's factor. Well, I don't have a constant here, but I do notice that I can pull out an x from both these terms. When I divide x out of negative x squared, I get negative x. And when I divide x out of 2x, I get plus 2. Check our work by distributing the x back in to see if we get the original equation. We do. Set each factor equal to 0. So one of my boundary points is going to be x equals 0. Negative x plus 2 is 0, so I'm going to subtract a 2 first. I'll still have negative x equals negative 2. Let's divide both sides by negative 1. So I end up with the other boundary point is positive 2. So I'm going to come over here and put x equals 0. That gives me a 0. X equals positive 2. Darken in that point. That gives me a 0. Those are the only two x-intercepts on this quadratic. So I have 3 test intervals. Okay, so next we have to just do test values. I think I'll put it right here. So let's see, the test interval, we'll do negative infinity up to 0. And negative infinity up to 0, I guess I'll just test x equals negative 1. So go to the equation. So f of negative 1 equals, and and you could plug in negative 1 to either one of these two. I guess I'll just plug it into the first one. That's negative outside. The x is negative 1. Let's square it. Plus 2 times negative 1. Well, that's going to be the power first. You can't distribute the negative inside this negative. You have to do the power. So that's positive 1, then it's made negative. I think that's going to be negative 3. And so what we see is that negative 3 is negative. So go back to this interval, and I plugged in x equals negative 1, but it returned a negative answer. So I'm just going to document a few negatives that way. All right, the next test interval will be from 0 to 2. So I guess the obvious choice is 1. So what's f of 1? I'm going to come back up here. Again, we'll do this on the calculator. I believe we get 1, and then 1 is positive. So we'll put a couple of plus signs in between x equals 0 and x equals 2. And then we're finally at our last interval, which goes from 2 to infinity. I guess I'm just going to try 3. So negatives outside, I'm going to square the 3, and then 2 times 3. So that's negative 9 plus 6. Negative 9 plus 6 is negative 3, and I'm back to negatives. I'm not going to say that every time we do this that the signs alternate, because it just depends upon the uniqueness of the equation. So it is important to do all the test values. Okay, so we're not done. We have to give our solution. So what's the solution? Well, am I choosing positives or negatives? Well, that's determined by the original problem. So let's take a peek back to the original problem. So this is f of x. We're looking for where f of x is greater than or equal to 0. So that would be right in here. So our solution would be 0 to 2. We're going to put brackets because we can include the zeros because of the or equal to. All right, so that's interval notation. All right, let's get a graph. So I'm going to build a number line. All I care about are the boundary points 0 and 2. And then I want everything in between 0 and 2. So I'll put 2 brackets that are facing each other and kind of highlight this section of the number line. All right, let's do one more example of solving a polynomial inequality. More specific, just quadratics is what we're going to restrict our view to. We're asked to solve this. Notice that one side is already set to 0 of this inequality, and even better yet, we've been presented with a nice little problem that's already been factored for us. So next step, let's set the polynomial equal to 0 to find the boundary point. So setting each factor equal to 0, we're going to get x equals 4, and we're going to get x equals negative 2. I think I'll come up here. This is where I'm going to organize my work. So really I have 2 number lines, one to organize my work and one to report the solution. So I'm going to put negative 2 and 4. So negative 2 is smaller than 4, so it goes here. And I'm going to darken those in, and then I'll put the zeros above them. All right, so I'm going to test in this first interval from negative infinity to negative 2, I'm going to test x equals negative 3. So f of negative 3 equals, so the original problem, if I plug in negative 3 here and negative 3 here, well, negative 3 minus 4 is negative 7. Negative 3 plus 2 is negative 1. I know when I multiply, that'll be a positive 7, and that's all I care about, is whether or not the result is positive or negative. So remember, x equals negative 3 comes from right here on the number line, so I get positive answers, so I'm just going to document some plus signs. All right, let's test another x value in this region right here, and I think 0 falls in between these two boundary points, so 0 is the better x value to choose. So let's go back to the original problem. So f of 0 So 0 minus 4 is negative 4, and 0 plus 2 is 2. I know when I multiply, I get a negative number. I don't care what it is, I just know it's negative. So between x equals negative 2 and 4, I'll put a few negatives here. Let me come up here because I'm running out of room. Let's test an x value in this last region. So I'll just test x equals 5. So f of 5, I'm back here. 5 minus 4 is 1, and 5 plus 2 is 7. So this is going to be positive again, so I'm going to get plus signs. All right, we're ready. We've done all the work. Now let's interpret and analyze our work number line here. All right, what's the solution? Well, I don't know. Am I choosing positives or negatives? It's not up to me to decide. I'm going to go back to the original problem, which is here. And remember, this is f of x greater than or equal to 0. So I want all the positives, including any zeros I see. So my solution is negative infinity to negative 2. Let's put a bracket because of the or equal. And union bracket 4 to infinity. All right, and let's organize this answer, this solution set on a number line. So we've got negative 2 and 4. Got a bracket going this way, bracket going this way, and we'll highlight these parts of the number line. Okay, you may be comfortable with this already, and that's great. Those are all the examples I have in this section, but in a different video, I will do some more practice problems. All right, we just solved some polynomial inequalities. Okay, we have two objectives in this section. Okay, and the second objective is to solve some rational inequalities. Doing the same thing that we've been doing with polynomials, but this time we're going to be dealing with fractions. So we'll do that in the next lesson.